Hello everyone, welcome back to this channel. In this video, we will build an MPC algorithm in MATLAB and Simulink. It uses this KBM model and the C GMRES solver. Here are the simulation results. The yellow line is steering angle delta, and the blue line is vehicle's acceleration. We will focus on the algorithm's engineering implementation, break down the C code architecture, also cover the core head file parameters. Industry chassis control requires decoupling and compilation. To meet these needs, the project is strictly divided into three core modules. First, the head file MPC model.h is the global definition hub for physical boundaries. Its core parameter configurations are as follows: n horizon and dt. They define the prediction steps and the control period. Their product determines the time depth of the feed-forward prediction. This directly impacts the foresight of the trajectory tracking. Next, DMX and DMU. They establish the dimension limits for system states and control variables. In this example, the state space is 4, and it defines FPY, StatF, FPX, and V. And the control space is 2. These are delta and acceleration. Next, LF and LR, they define the inherent kinematic parameters. This includes the vehicle's front and rear wheelbase. The source file MPC model.c acts as a pure math engine. Its engineering purpose is to hide the cost weight matrix Q, SF, and R. This prevents global variable pollution. It mainly implements two things internally: the forward integrate calculation of the state equation x dot based on the KBM model. Secondly, the backward difference calculation of the variable lambda. This is based on the partial derivative of the Hamiltonian. Alright, next, the head file cgmres solver.h. This controls the solver's limits and convergency. Here are the core parameter configurations. First, Kmax. This defines the maximum iterations for the Cry-law subspace in the GMRES algorithm. You must carefully balance calculation cost against the approximation accuracy here. Next, zeta. This defines the stabilization constant in the process. It determines how fast the nonlinear equation residual decays over time. This directly affects the system's dynamic tracking pose. Alright, next, cgmres solver.h. This file encapsulates all low-level numerical solving logic. Next, MPC rep.c. It is a standard Simulink S-function interface. It connects the C code computing engine with the outer simulation framework. Note here, the state inputs 4 dimension and the control outputs 2 dimension. These map with this here. Alright, these files all have their own specific duties. Once you compile them together in MATLAB using the max command, they integrate into Simulink. And I build a Simulink model like this. First, let's input this in Commander window. Max MPC rep.c MPC model C and cgmres solver.c. You can, when you see max completely successful, so this means our files are all work. Then we open the Simulink. I will show you how to build this model. First, here, input S function. as function, double click it, and input MPC wrapper. Okay, so here input marks, double click it. The number of input is 4. Enlarge it. Then here, the input first we use sine wave. Okay, this represents the FPY. And next, the rest of 4 parameters we use constant. Okay, let me enlarge this. And this is 0. And the next is constant 2. And the FPY is also 0. The last one is the speed. It is also constant. Okay. And the speed is 10. Then we connect all the inputs into the max. Connect to the S function. And here, this is FPY. Double click here. This is set F. Double click here. This is FPX. And double click here. This is speed V. Okay. The output here. This is the max. Connected to the wrapper. And we build a scope. So we can see the outer curve. The scope. Double click it. So in the setting, the input ports, 2 input ports, connect. Okay, enlarge it. So this is delta steering wheel angle, and this is acceleration A. Okay, so now we build this model. Right. And right. Let's see the result. So you can see there are 2 lines. Let me arrange it. Layout. Okay. And let me show the legend. And adjust the style. The delta, we use yellow color. And the acceleration, we use blue color. Okay. All right, let's see the result. The yellow line is vehicle steering wheel angle delta. Since the FPY input is sine wave, so the algorithm outputs a reverse steering command to correct the deviation. You will notice this line has a subtle stair-step effort. It's because we set the control period to 0.01 seconds in our code. This perfectly illustrates the classic zero-out hold phenomenon found in digital control systems. The blue line is vehicle's acceleration. Because the reference speed and the current speed are or exactly 10. So the acceleration is always 0. Alright. I uploaded the MATLAB code to GitHub, so feel free to download it yourself. Over the past 6 episodes, we have successfully reproduced this paper. This includes the modeling of the dBm and kBm in the FS coordinate system, as well as the implementation of the MPC algorithm. If you have any questions, please leave a comment below the video. I am Kevin. See you next time.